Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about distance, rate, time, word problems.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. A container ship left the Dania Pier and traveled north. An aircraft carrier left 4 hours later, traveling at 30 miles per hour in an effort to catch up to the container ship. After traveling for 8 hours, the aircraft carrier finally caught up. What was the container ship's average speed? So we need to break down two distance, rate, time problems here. Okay? So the container ship, we'll call it the distance of the container ship travel equals the rate of the container ship times time of the container ship. We can do the same thing with the aircraft carrier. Okay? Alright, so let's go plug in what we, know here. They said the aircraft carrier left 4 hours later, traveling 30 miles per hour. So its rate is 30 miles per hour for the aircraft carrier. Okay? Now, it left 4 hours later, and then after traveling 8 hours, it caught up to the container ship. So the total time the container ship was out there is the 8 hours from the aircraft carrier plus the original 4 hours later. So the aircraft carrier traveled 4 hours after the container ship and took it 8 hours to get there. So the overall time would be 8 plus 4 for the container ship, and the aircraft carrier would be 8 hours here. That's equal to the distance here. And what we want to find is the rate of the aircraft carrier, or the container ship, sorry. Well, notice here, D sub C and D sub A are referring to actually the same distance. We're trying to find, all this information came to us, giving us at a point where they met. So they must have traveled the same distance. So now DC and DA are, equal to each other. And so by doing that, we can set these two equations equal to each other. So we have RC sub C of 8 plus 4, that's 12, is equal to 30 times 8. 30 times 8 is 240. We have RC times 12 here. Divide 12 to both sides, and the rate of the container ship is 240 divided by 12 is 20, and our units are miles per hour. And so the container ship's average speed was 20 miles per hour. We're given this problem right here. A cruise ship made a trip to Guam and back. The trip there took 12 hours, and the trip back took 9 hours. It averaged 20 kilometers per hour on the return trip. Find the average speed of the trip there. So we have our cruise ship, and we're gonna break this down to the trip there and the trip back. So our distance equals rate times time. We'll separate the distance of going there, call it t, sub t, is the rate of sub t times t, little t, of sub t. And then back is distance of the back journey is equal to the rate of the back journey times the time of the back journey. Okay? So we're going to use that to try to plug in what, we know from the problem here. The trip there took 12 hours. So we know that the trip there, t sub little t, being there, took 12 hours. And we want to find the average speed getting there, the rate at which we traveled there, so that's still our variable, r of t. And that's equal to d sub t. So d sub b, what is that equal to? Well, they tell us that the return trip rate was 20 kilometers per hour. So we're going to put a 20 here. And it took us, 9 hours, right? Let me find that, yeah. The return trip back home took 9 hours. And so now we have two equations that we actually can set equal, because the distance there is equal to the distance back. It's the same distance. So let's set them equal to each other. R sub t times 12 is equal to 20 times 9. Well, r sub t times 12 is, r sub t times 12. Now let's simplify that 20 times 9, which is 180. And if we divide 12 to both sides here, we have the rate going there is equal to 180 divided by 12, which is 15, and that the units there is kilometers per hour. And so the average speed there was 15 kilometers per hour. We're given this problem right here. Scott left the airport and traveled toward the train station. 3 hours later, Castile left traveling at 50 miles per hour in an effort to catch up to Scott. After traveling for 2 hours, Castile finally caught up. What was Scott's average speed? Well, we know our formula, distance equals rate times time. So we're going to break it down for, well, distance of Scott is equal to rate of Scott times time of Scott. And we're going to do the same thing for Castile. Distance of Castile equals the rate of Castile times the time of Castile. Okay. Well, what do we know from our problem here? Okay, and this is going to be a little tricky. They tell us that 3 hours after Castile left, traveling, 50 miles an hour, Scott went. Okay? Oh, sorry, Scott left first, and then 3 hours later, Castile left. And it took him 2 hours to catch up. So Castile was only traveling for 2 hours. Scott's time was that 2 hours, or initially 3 hours, then the 2 hours till Castile caught up. So it's 3 plus 2 here. Now, we want to find Scott's speed or Scott's rate. So that's going to stay right here. We don't know that. Well, what's the rate of Castile? They tell us that Castile traveled 50 miles per hour. Okay? Now notice here we have distance of Scott and the distance of Castile. These distances, we don't know actually what that distance is, but we know they're the same. They both start at the same spot and ended at the same spot. So that means we can set these two equations equal to each other. So we have R of S, rate of Scott, 3 plus 2 here, is equal to 50 times 2. Let's simplify this a little. We have rate of Scott times 3 plus 2, 5. And 50 times 2 is, 100. To get the rate of Scott by itself, we divide both sides by 5. And then we have R of S, not Castile, but Scott, is by itself. And 100 divided by 5 is 20, and our units here is miles per hour. And so Scott's average speed was 20 miles per hour. We're given this problem right here. Jose traveled to the town hall and back. The trip there took 5 hours, and the trip back took 4 hours. He averaged 35 kilometers per hour on the return trip. Find the average speed of the trip there. So we know our formula, distance equals rate times time. But we're going to break it down into 2 sections. Distance there, being t, is equal to the rate there times time there. And we're going to do the same thing with the trip back for Jose. Distance back is equal to the rate back times time back. So now we're going to take these 2 formulas and plug in what we can from our problem here. Well, they tell us there that the trip took 5 hours there. So t sub little t is 5. And we actually want to find the average speed there, or r of t. And we don't actually know the distance there. And we actually don't know the distance back either. But they tell us here that the average speed there, or on the return trip back home, was 35 kilometers per hour, and it took a total of 4 hours to get back. And so now we actually have enough information to solve. We don't know what the distance there was or the distance back, but what we do know is that they're equal. It's the same distance. So we can set these 2 equations equal to each other. R sub t of 5 is equal to 35 times 4. Let's simplify this a little. R of t times 5, and 35 times 4 is 140. Divide 5 to both sides, and we get the rate there is equal to 140 divided by 5, which is 28, and our units is kilometers per hour. And so the average speed of the trip there was 28 kilometers per hour. We're given this problem right here. Perry left school driving toward the lake 1 hour before JD. JD drove in the opposite direction, going 6 miles per hour slower than Perry for 1 hour, after which time they were 174 miles apart. What was Perry's speed? This is a tricky one. So we're going to break this down to two distance, rate, time equations. Distance of Perry is equal to the rate of Perry times the time of Perry. The distance of JD is equal to the rate of JD times the time of JD. So we're now going to put in, well, what we know and what we need to find. So they tell us here that JD drove in Perry left an hour before JD. Okay, and then at the end time happens. Well, if it's an hour before and then whatever time JD goes, that means Perry's time we can write in terms of JD. It is 1 hour plus JD's time, T of JD, and that's the total time that Perry was there, 1 plus the hour of JD. Now, we want to find Perry's speed, so that just comes down here. And, well, we don't know necessarily the distance individually of Perry. Okay, so we're going to hold off on that for a second. Now let's go with what we know here. They tell us that JD drove in the opposite direction, but going 6 miles per hour slower than Perry. So JD's rate can be rewritten as the rate of Perry's minus 6 miles per hour. If it was 6 miles per hour slower. And we don't know, well, JD's time yet. Alright, so we'd leave that there, the time of JD. But one thing they do tell us here, and this is the little kicker here, is that they say that after all this, there were 174 miles apart. So that means their distance, d of p, plus d of t, is equal to 174. Okay? Alright, there's actually one more thing I missed. Let me make sure I catch it here. They said with JD, right? JD drove the opposite direction, going 6 miles per hour slower than Perry for 1 hour, after which time they were 174 miles per hour. So JD was only driving for 1 hour, right here, meaning we can figure that out here, right? This time of JD is just 1. So let's simplify what we can. There's d of p here. Keep that a little separate. And we have d of j. So let's rewrite what we can, just make it a little simpler. D of Perry is the rate of Perry, and 1 plus 1 is 2. Okay. Well, multiplying this out, d of j is, well, all this times 1, r of p minus 6. So we can simplify. Distance of JD is r of p minus 6. And that's where it gets a little tricky, okay? We can rewrite d of p equal to, if we subtract dt to both sides, d of p is equal to 174 minus j, the distance of, d of j, that's a j here. Distance of JD. And so we can use that and actually plug it into this equation right here. So instead of d of p, we're going to write that 174 minus d of j is equal to r of p times 2. Okay. Well, we also know d of j is equal to rp minus 6. So let's replace that now here. So we have 174 minus rp minus 6 is equal to r sub p of 2. Or times 2. So let's rewrite what we can. If we distribute this minus sign, it's plus a negative, and this becomes a positive. 174 plus 6 is 180. And we have a minus r sub p is equal to, we can rewrite that to have 2 comes first, makes it easier to see, times r of p. If we add an r sub p to both sides, what are we left with? Well, let's go put it right up here. We have 180 is equal to, well, 2 plus 1 is 3, so 3 of r sub p. And now we want to divide 3 to both sides to get r sub p by itself. So r sub p is equal to 180 divided by 3, which is 60 units, miles per hour. And so Perry's speed at that time, after all that, was 60 miles per hour. We're given this problem right here. Wilbur left the hardware store and traveled toward the recycling plant at an average speed of 33 kilometers per hour. Mary left 2 hours later and traveled in the same direction, but with an average speed of 55 kilometers per hour. How long did Wilbur travel before Mary caught up? So let's go break down distance, rate, time equations for both Wilbur and Mary. So distance of Wilbur is equal to the rate of Wilbur times the time of Wilbur. The distance of Mary is equal to the rate of Mary times the time of Mary. Okay? So let's plug in what we know. They tell us Wilbur traveled at an average rate of 33 kilometers per hour. So that's pretty easy there. They tell us that Mary traveled at a rate of 55 miles per hour. Or kilometers per hour. Okay? But then, what about our time? Okay? They tell us that Mary left 2 hours later and traveled in the same direction. But we don't know actually how long Wilbur was traveling. That's really what we're trying to find here. So, the T of W, we don't know, but T of Mary, we actually can write in terms of Wilbur's. Whatever Wilbur's total time was, if we subtract the 2 hours, we would get the time that Mary was traveling. And so we have dW here and dm right there. All right, so where do we go from here? Well, their distances, because we're finding where Mary caught up to Wilbur, that distance is going to be overall the same. So we can set these two equations now equal to each other. 33 times t sub w is equal to 55 times t sub w minus 2. So let's go distribute this 55 over. So 33 times t sub w is equal to 55 t sub, not sub t, t sub w, t sub w, minus 55 times 2 is 110. Well, we want to combine our like terms, subtract a 55 t sub w to both sides. And 33 minus 55 is a negative 22. T sub w is equal to negative 110. Let's divide a negative 22 to both sides here. And we have the time that Wilbur was traveling, it's going to be positive, is negative 110 divided by negative 22, which is 5, and our unit is hours. And so Wilbur was traveling for 5 hours before Mary caught up. I'm given this problem right here. An aircraft carrier left Hawaii traveling west 7 hours before a container ship. The container ship traveled in the opposite direction, going 5 kilometers per hour slower than the aircraft carrier for 6 hours, after which time the ships were 540 kilometers apart. Find the aircraft carrier's speed. So these are distance, rate, time problems. Let's go separate it up here. The distance of the aircraft carrier is equal to the rate of the aircraft carrier times the time of the aircraft carrier. The distance of the container ship is equal to the rate of the container ship times the time of the container ship. So let's plug in what we, know here. What about time? Well, they tell us here an aircraft carrier left Hawaii traveling west 7 hours before the container ship, and then they, 7 hours. So that 7 hours is here, and the time for the aircraft carrier. But then later on they tell us here that the container ship was leaving for 6 hours after. So after 7 hours, then the container ship left for 6 hours. So the total time for the aircraft carrier out in the water is 7 plus that 6. Okay? And so now we know the time the container ship was out was only 6 hours. Okay, what about their rates? Well, we don't know the rate of the aircraft carrier. But we do know, they tell us this key thing, the container ship was traveling the opposite direction 5 kilometers per hour slower than the aircraft carrier. So the rate of the container ship is whatever the rate of the aircraft carrier is minus 5. And bring down the d sub c and bring down the d sub a. Now there's one more thing they tell us here. They said after all of this, the ships were 540 kilometers apart. Now remember, they're going in opposite directions. So that means if we add their distances, distance of the aircraft carrier plus the distance of the container ship is equal to 540 miles. If we get d of a by itself, d of a is equal to, we'll subtract dc to both sides, d sub c. It's 540 minus d sub c. So let's go simplify these a little bit if we can. D sub a is equal to, well, r of a times 7 plus 6, which is 13. So let's go 13 r sub a. Same thing with d sub c. Let's distribute that 6 across. 6 times ra is 6 r sub a, and minus, well, 5 times 6 is 30. Okay. Well, they tell us here that d sub a is equal to 540, or we found 540 minus d sub c. So let's try to get things in the similar terms. So let's go replace that. 540 here minus d sub c is equal to 13 r sub a. Let's get d sub c by itself. Subtract a 540 to both sides, and we have a negative d sub c is equal to 13 ra minus 540. If we want to bring this negative over to the other side, we have d sub c equals a negative 13 r sub a, and then that's a positive 540. Now this becomes helpful because we can use that for this d sub c. D sub c is equal to, well, negative 13 r sub a plus 540 equals the 6 r sub a minus 30. And now we have the equation here where we just have our variable r sub a that we need to find, the rate of the aircraft carrier. So let's try to get that by itself. If we add a 13 r sub a to both sides, and we can add a 30, let's put our like terms together to both sides. 540 plus 30 is 570, and 6 plus 13 is 19. So we have 19 r sub a. We now divide by 19 on both sides. And let's put r sub a first. And 570 divided by 19 is 30, and our units is kilometers per hour. And so the aircraft carrier speed is 30 kilometers per hour. We're given this problem right here. A submarine left the Azores and traveled west. 3 hours later, an aircraft carrier left traveling 3 miles per hour faster in an effort to catch up to it. After 7 hours, the aircraft carrier finally caught up. Find the submarine's average speed. Okay. Well, we know distance equals rate times time. So we're going to set this up as distance of the submarine is equal to the rate of the submarine times the time of the submarine. And the distance of the aircraft carrier, right, is equal to the rate of the aircraft carrier times the time of the aircraft carrier. And now we're going to try to plug in what? Well, we know. So the submarine first left, then 3 hours later, the aircraft carrier left. And after 7 hours, the aircraft carrier finally caught up. So the aircraft carrier was only in the water for 7 hours, or traveling for 7 hours. The submarine started 3 hours earlier, then after 7 hours, aircraft carrier caught up to it. So we combine those hours together here. Now, they don't really tell us here what the rate of the submarine is. But they tell us something about the aircraft carrier. They say the aircraft carrier was traveling 3 miles per hour faster than the submarine. So the aircraft carrier's rate can be written in terms of the submarine. Rate of the submarine plus 3 miles per hour. And that's equal to the distance of the aircraft carrier and distance of the submarine. Well, what is the distance of the submarine and the distance of the aircraft carrier? We don't know that. But what we do know is that they're going to be the same distance. because they both left from the same place, and eventually this aircraft carrier caught up to it, and whatever that distance is, it's going to be the same. So we can set these two equations equal to each other. R of S is equal to 3 plus 7 is equal to R of S plus 3 times 7. And this actually becomes pretty beneficial here now. We only have one variable that we have to solve for, and it's a variable we're looking for. So R sub S is equal to 3 plus 7, which is 10. Distribute the 7 across right here. 7 times R of S here, and 3 times 7 is 21. Well, let's try to combine our like terms. Now this is 10S, or 10 times R of S. If we subtract a 7 from that, it's kind of hard to see, but kind of it's flipped around, but you can imagine the 10's on the outside here. And 10 minus 7 is 3. So 3R sub S is equal to 21. Divide both sides by 3, and R sub S is equal to 21 divided by 3, which is 7, and our units is miles per hour. And there we have it. The submarine's average speed was 7 miles per hour. We're given this problem right here. Jimmy drove to his cabin on the lake and back. It took 0.6 hours longer to go there than it did to come back. The average speed on the trip there was 46 kilometers per hour. The average speed on the way back was 52 kilometers per hour. How many hours did the trip there take? So let's break it down to two equations. Distance there is equal to the rate there times the time there. The distance back is equal to the rate back times the time back. And so let's plug in, well, what we know. They tell us here that the average speed there was 46 kilometers per hour, and the average speed on the way back was 52 kilometers per hour. Okay? Now, they also tell us that it took 0.6 hours longer to go there than it did to come back. So going there is 0.6 plus the time back. And we don't know that, what the time back was. And so we have the distance there and the distance back. Well, one thing we do know though, the distance there is the same thing as the distance coming back. And so these two equations can be set equal to each other. So we do that, 46 times 0.6 plus t sub b is equal to 52 times t sub b. And now we just have one variable, so let's solve for the distance, or the time coming back. Distribute the 46 across, and 46 times 0.6 is 27.6. Plus 46 times t sub b is just 46 t sub b. And that's equal to 52 times t sub b. Well, we can subtract a 46 to both sides, or t sub b, to get our like terms together. And we're left with that 27.6 is just left over here, is equal to 52 minus 46, which is 6. There's 6 times t sub b. We divide both sides by 6, and we're left with, well, t sub b, let's put it here, is equal to 27.6 divided by 6 is 4.6. But that's the time back. They're asking us how long did it take to go there. So we know that the trip there, the time there, is equal to 0.6 plus the time back. Time back right here, we said was 4.6, so time there is equal to 0.6 plus 4.6 hours, and 0.6 hours plus 4.6 is a total of 5.2 hours. And there we have it. The trip there took 5.2 hours. We're given this problem right here. Anjali traveled to the recycling plant and back. The trip there took 5.8 hours, and the trip back took 5.1 hours. She averaged 7 miles per hour faster on the return trip than on the outbound trip. what was Anjali's average speed on the outbound trip? So we know this is distance equals rate times time. Let's break it down to be distance there is equal to the rate there times the time there. And the distance back is equal to the rate back times the time coming back. And so what do we know? Well, it's the trip there took 5.8 hours, so let's plug that in for the trip, the time there. And the trip back took, well, 5.1 hours. Okay. What else do we know? Well, we want to find Anjali's average rate on the trip there, the outbound trip going there. So that variable is going to stay right here. But she averaged 7 miles per hour faster on the return. So that's right here, the trip back. Well, she was 7 miles per hour faster. It's the original speed's trip there, the rate, r sub t plus 7 is the speed of the rate returning. So bring down d sub b, and then bring down d sub t. Okay, well, the distance there and the distance back is going to be the same. It's the same distance. So we can set these two equations equal to each other. So we have r sub t times 5.6 is equal to, right here, r here, I was flipping around, r sub t plus 7 times 5.1. And so let's simplify where we can. Okay, oh, I messed up, sorry. Hopefully, if you caught this, let me know. This is an 8. I can rewrite, this is an 8. So if you're watching this video and you're like, wait a minute, he made a mistake. I did. But it's okay, we all make mistakes, so I fixed it here though. So we learned from it. It's 5.8 hours there, not 5.6. It's important to be careful when dealing with word problems. Take your time. So luckily I caught it though. And again, if you caught it, let me know down below. Alright, so 5.8 times RT equals this. Alright, let's go distribute this 5.1 out here. So we have 5.8, I'm going to rewrite here, I almost wrote 5.6 again, times RT is equal to 5.1 times R sub t plus 5.1 times 7, which is 35.7 here. Let's get our like terms together. So we're going to subtract a 5.1 R sub t to both sides. And 5.8 minus 5.1 is 0.7 R sub t, and that's equal to 35.7 here. Divide both sides by 0.7, and what do we have? Well, R sub t is equal to 35.7 divided by 0.7, or 0.7, right? It's 51, and our units is miles per hour. And so Anjali's average speed on the outbound trip going there was 51 miles per hour. We're given this problem right here. A fishing boat left Hawaii traveling west 0.5 hours before a cruise ship. The cruise ship traveled in the opposite direction, going 12.5 kilometers per hour faster than the fishing boat for 11 hours, after which the time the ships were 322 kilometers apart. A lot packed in that sentence. What was the fishing boat's speed? Okay. Well, we'll start with distance equals rate times time for each one. Distance of the fishing boat is equal to the rate of the fishing boat times the time of the fishing boat. And the same thing then with the cruise ship. Distance of the cruise ship is equal to the rate of the cruise ship times the time of the cruise ship. So let's plug in what we, well, know. So the fishing boat, right, so let's go down. The cruise ship left later, all right, 0.5 hours later, and traveled a total of 11 hours. So the time of the cruise ship is 11 hours. The fishing boat was left 0.5 hours earlier, so it's 0.5 plus that 11 hours. And that's the time the fishing boat was out there. Well, we want to find the fishing boat's speed, its rate, so we don't know that here. And bring down the distance, we don't know that either. But the rate of the cruise ship, they give us a clue. They tell us here that the cruise ship was traveled in the opposite direction, but was going 12.5 kilometers per hour faster than the fishing boat. So the rate of the cruise ship can be written as 12.5 plus the rate of the fishing boat. And that's equal to d sub c. We're almost there. They give us one other clue. They say at the end of all of this, the fishing boats were 322 kilometers apart, and they're going opposite directions. So if we add their distance traveled, distance of the fishing boat plus the distance of the cruise ship, that's going to equal 322. And so if we subtract a d sub f to both sides, we get the distance of the cruise ship is equal to 322 minus distance of the fishing boat. So now what we're going to do, all right, let's go simplify what we can a little bit here. All right, I can simplify some of this stuff out. So d sub f is equal to, well, r sub f times 0.5 plus 11 is 11.5. Not too much going on there. Distance of the cruise ship, if we distribute the 11 across here, 11 times 12.5 is 137.5 plus 11 r sub f, the rate of the fishing boat. Okay. Okay. Well, we found d sub c is equal to 322 minus d sub f. So I can replace that here. So instead of d sub c, I'm going to write 322 minus d sub f is equal to 137.5 plus 11 times r sub f. So now we have an equation with only one, almost one variable. All right, we have two variables, d sub f and r of f. But d sub f we can write here, right? This whole thing we can put in for that d sub f now. So let's do that as well. We have 322 minus d sub f, which is r sub f times 11.5, let's put it in parentheses, double parentheses, is equal to 137.5 plus 11r sub f. And actually now we only have an equation with one variable, r sub f, which is actually the variable we want to find. So now we actually, after all of that, we can solve this. Okay, let's go clean this. I'm going to rewrite this a little bit. 322 minus, I'm going to put 11.5 first so it's clear, r sub f is equal to 137.5 plus 11r sub f. Let's bring our like terms together. I'm going to add 11.5 r sub f to both sides here. And then I'm going to subtract a 137.5, put it to the other side. 322 minus 137.5 is a 184.5. These cancel, and these will cancel. And that's equal to 11 r sub f plus 11.5 r sub f is a 22.5 r sub f. We divide 22.5 to both sides. And what do we have? Well, r sub f by itself here is equal to 184.5 divided by 22.5 is an 8.2, and our units is kilometers per hour. And so the fishing boat's speed was 8.2 kilometers per hour. I'm given this problem. A diesel train left the station traveling north 1.5 hours before a freight train. The freight train traveled in the opposite direction, going 6 kilometers per hour faster than the diesel train for 2 hours, after which time the trains were 312.3 kilometers apart. Find the diesel train's speed. Well, distance equals rate times time here. So let's write this equation for both the diesel train and the freight train. The distance of the diesel train is equal to the rate of the diesel train times the time of the diesel train. The distance of the freight train is equal to the rate of the freight train times the time of the freight train. So let's plug in what we know and what we can, well, deduce a little here. Okay. The freight train, so the diesel train left the station traveling north 1.4 hours before the freight train. The freight train was traveling the opposite direction, they say, for 2 hours. So the time of the freight train is just 2 hours here. Not too bad. For the time of the diesel train left 1.5 hours beforehand, so it's 1.5 plus the 2 hours to get the overall time the diesel train was out there. Okay. Now we want to find the rate of the diesel train, so we don't know that. And the distance of the diesel train, we don't know either. But what about the rate of the freight train? They say the freight train is traveling in the opposite direction, but 6 kilometers per hour faster than the diesel train. So the rate of the freight train can be written as the rate of the diesel train plus 6. And let's bring down this, the distance of the freight train. Now we're almost done setting up everything. There's one more clue they tell us. They say after this whole thing happened, the trains were 312.3 kilometers apart, and they're traveling in opposite directions. So the distance of the diesel train plus the distance of the freight train is equal to 312.3 kilometers. We can adjust this by subtracting the distance of the freight train to both sides. And so the distance of the diesel train is 2. Oh, I'm getting ahead of myself here. What is skipping numbers? It happens. It's okay. Distance of the diesel train is equal to 312.3 minus distance of the freight train. So now we have all these different equations. What can we do with that? Well, what I can do is, well, I don't know. I'm going to take, what am I doing here? First, let's make sure I'm doing everything right here. Okay, let's simplify. That's what I want to do, simplify first. The distance of the diesel train is equal to the rate of the diesel train, and then 1.5 plus 2 is 3.5. Here, distance of the freight train is equal to, distribute the 2 times the rate of the diesel train, plus 2 times 6, which is 12. Okay? All right. Well, we know the distance of the diesel train is equal to 312.3 minus distance of the freight train. So I'm going to replace that here, and I have 312.3 minus distance of the freight train is equal to, let's rewrite this, 3.5 rate of the diesel train. Okay? So now let's get our distance of the freight train by itself, this variable. I'm going to subtract the 312.3 to both sides. And we have a negative distance of the freight train is equal to 3.5 rate of the diesel train minus 312. Well, that's a 2.3. Okay. Now this negative we bring over to this side to make distance of the freight train positive, and that's a negative 3.5 rate of the diesel train plus now 312.3. After all that, we know distance of the freight train, we can plug it in here. So we're going to take all of this that we found and we're substituting it in for the distance of the freight train. So in doing so, we have a negative 3.5 rate of the diesel train plus 312.3 is equal to 2 times the rate of the diesel train plus 12. And actually we're pretty happy here. We have one equation now which gives us, or the only variable is the rate of the diesel train, and that's what we want to find. So we're going to combine our like terms here. I'm going to add a 3.5 rate of the diesel train to both sides. And this will cancel out. And I'm going to subtract 12 to both sides. That will cancel out. And so 312.3 minus 12 is 300.3. And 2 plus 3.5 is a 5.5. And that's being multiplied by r sub d. If I divide both sides by 5.5, I'm left with r sub d by itself here is equal to 300.3 divided by 5.5 is a 54.6, and our unit is kilometers per hour. And so the diesel train speed is 54.6 kilometers per hour. I hope this video was helpful, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, When you need help, you use Minute Math. Minute Math, Minute Math. When you need help, you use Minute Math. MinuteMathTutor.com.